Good day, everyone. My name is Kamzar Rahman, and today I will be presenting our research work on the computational structure analysis of a modified knee implant design for total knee replacement. This research was done as part of our final year project as undergraduate mechanical engineering students in the University of Engineering and Technology, Lahore, Pakistan. The aims and objectives of our research was to compare the contact pressures of a modified concentric tibial insert with that of a standard total limb replacement design, while emulating actual knee biomechanics. To achieve these objectives, we first procured the 3D scan data of an actual knee implant. We then used reverse engineering to obtain the CAD models of the standard TKR design, and then we also modified that design for a modification such that the tibial insert contours were directly concentric with that of the femoral component contours. We then used computational analysis on both of these designs and then validated the finite element analysis methodology and results of both of the design in comparison with those of published literature. So basically, the incidence rate of TKR is expected to increase to 143% by 2050 in the US alone. This thus necessitates the enhancements and further working on the specific focus of increasing the implant life cycle of an orthopedic implants such as knee implants. The life expectancy of a total knee replacement standard design is 25 years with a revision and 10 to 15 years without revision. The contributing factors towards its life cycle are the aseptic loosening and the wear of the tibial insert. Specifically in this research, we will be focusing on the wear of the tibial insert and to understand that better. As designers, our focus is primarily to simulate the anatomic knee contours of the computational model as closely as possible, and is to study the biocompatibility of materials as well. But in this research alone, we will be only focusing on the anatomic accuracy of the CAD model. The implant testing is done in which we, in the computational design stage, primarily what we do is we are looking for a preliminary design elimination process in which we filter out our designs before they are sent for a more expensive and more time and cost intensive experimental analysis, right? So in these computational analysis stage, we focus on the actual contact pressures between the femoral component, which is the thigh bone, the part that is attached to the thigh bone, and the tibial insert component, which is attached to the shin bone, right? So to do this, when we study and monitor the contact pressures, we can actually predict the wear rate of the tibial insert as well as desiredly proportional to the contact pressure. So the methodology. To do this, first of all, we use the reverse geometric model. We reverse engineered the open source implant scan data. This was done separately for the femoral component and then for the tibial component. And then both of these models were assembled together in SolidWorks. So this is a small video of how the design overall of our final design and how everything was done. First of all, we made the contours, and then the gray portion is the part that is being made, traced out of this multicolored, multi-bodied scan data that is divided into multicolored zone regions. So this is our final design for the femoral component. As for the tibial component, we can see that this is our design. And this is how we used mesh and body sketch techniques for reverse engineering our model. Over here, we can also see that the tibial component of the modified tibial implant insert was made by such that we use the femoral component to carve out the cavities of the tibial insert so as to emulate how exactly a plastic or a softer cartilage tibial insert would envelop or be bound to the femoral component when it is fully loaded, right? So this is why we went for this modification, and we wanted to check and we wanted to see which of the both designs was better able to depict the actual anatomic loading conditions of a total knee replacement. So this is how our computational analysis was done. We first applied the boundary conditions. We made sure that the tibial in the lower portion of the lower face of the tibial insert was stationary, similar to how it would be in a knee. And then the femoral component was loaded with a vertical load of approximately 1.7 kilonewtons. This load is actually the maximum amount of contact forces that are in action on the on our knee joint when we talk about this specific patient, as taken from the research paper that used the same patient specific and the same scan data in their multi-body skeletal system, right? So later we applied the muscle slave interaction properties on our implant model, and then we applied a 0.04 penalty contact for the friction properties. We also applied tetrahedral meshing for the whole assembly with 2 millimeter sleeve size. The materials that we used were the cobalt chromium molybdenum alloy for the femoral component and the ultra high molecular weight polyethylene plastic for the tibial insert, which is also all of these properties are from the standard materials that are used for typically for a total knee replacement design that we took as a source. So these are the results finally. So we can see that this initial result is it talks about the geometric accuracy of the reverse engineering that we did. So this basically is something that was not really done before, while there were researchers that talked about generating generating accurate PKR designs by reverse engineering, but there was no asset quantification of total knee replacements and how much and the accuracy of the reverse engineering that was done in the computational models. So this is in essence one of our major results as well, because we have used geometric design X and the deviation for body plots in the software to depict the quantifiable differences between the geometry that we made and the geometry of the source scan data. We can see that the yellow portions are the portions that will be in contact, will be articulating when the knee is moving. So these are the parts that were made to be most accurate, meaning they were within the 0.001 millimeter accuracy that we were going for. Next, this is the result for our static model. This static model depicts that the validity of our initial finite element analysis framework for the standard TKR design. What we did was we compared the results of our result under the maximum point load of 1.7 kilonewton to that of a complex multi-body dynamic model that was taken out by Zhang et al. And we found out that there was only 10% difference between both of these results, and such. So we validated our finite element analysis framework as a valid one, right? Then finally, what's the catch? What's new, and what did we achieve by this modification, right? You can see that in both of these designs, the primary difference is that the distribution of the stresses, right? The modified TKR design has a greater, more symmetrical distribution for both of these on both condyles, which are the both contacting part. Secondly, we also see that while the standard TKR design, which was used as is, had a tangential contact, it would mean that it would have more localized stresses. Thus, we can also see that it has 15.28 megapascal maximum contact pressure, while the modified only has 3.37 megapascal, which is like 78% lower than that of the standard design, right? The third achievement that we achieved was that we compared the results of our computational model with the strain mapping of cartilages that was done by previous researchers through MRI scans. we found that our modified TKR design was in closer proximity with the anatomical stresses and the cartilage strain mapping of an actual anatomic knee. Thus, we found out that our modified TKR, the TKR, modified TKR design was in greater proximity and closely exhibited the accurate anatomic conditions in that of an actual knee implant, right? So what are the conclusions? So the key outcomes of our research were first that we were able to quantify the accuracy of our CAD model, the extent to which our reverse engineering was accurate, was up to 0.001 millimeter and within these tolerances. Secondly, we found out that the finite element model that we used was within 10% of the published literature results, which also meant that our model was thus validated. Thirdly, we concluded that the modified CQR design not only did it more closely detect the anatomic strain and stresses of an actual knee implant, but it also decreases the contact pressure by 78% rather than the contact pressure of the standard design. So thus these are the conclusions. These are the references that we use. The first reference, and these are the couple of references that if you guys want, you can also contact us again, or you can just like jot these down from Google Scholar and view these pages for the references that we use. So that's all from my side. Thank you so much for your attention. The house will be open for any questions. Please let me know if there is anything that I can clarify. Thank you.